Coach Carroll back here to coach you through 2D vector addition using the algebraic approach and coach you at life as well, guys. Here we go. The previous video over this homework set, we've already done the graphical, there we go. We've already done the graphical approach to this problem. And this video will go over the algebraic approach. That's where we will use component form of vectors. So just to review, this problem asks us to add the two vectors A and vector B to get the resultant. Now we're asked for the magnitude of the resultant, and we're also asked for the angle, we're asked for the angle theta x that the resultant makes with the positive x-axis. Okay, so overall, in the algebraic solution of addition of vectors, the general approach is to write each vector into component form. There's A in component form, so ax I hat, it would be the x component, and here is the y component. So let's draw what those look like. So there's vector A, the x component, there's the x component. It's the projection of the vector onto the x-axis. That's the x component. So what's the projection of vector A onto the y-axis? It's right there. There's a y. Now notice the vector A is the addition of the x component and the y component. So if we add the x component and the y component graphically, both here start. Trying to get used to this nice little graphics pad right here that makes this all possible. Still fresh at it. Okay, so if you look at the addition of the two components, both components have their tails start at the same place. So if I make a parallelogram using the components, which turns out to be a rectangle because the components are perpendicular, connected diagonal, and there's vector A. Okay? Now, just to review, what is I hat? Well, I hat is a unit vector, and any unit vector has a length of 1, but I hat is a special unit vector that points in the positive x direction. So this would be I hat. Now, why do I say hat? I'm saying hat because I write it with that little hat over it, kind of like I'm wearing today in honor of I hats, talking about unit vectors. So I hat is a unit vector. Remember, unit vector has a length, or magnitude, equal to 1. Okay. Now what is j hat? J hat is a unit vector in the positive y direction. That is j hat. And again, it's a unit vector, so it has a length of 1. Okay? Now, we know the magnitude of vector A is 10 units. Okay? Now, how do we know the direction? The direction is shown by this triangle. Directions can be shown in various ways, and for vector A they show it with this 3, 4, 5 triangle, and the reason I know that's 5 is just with Pythagorean theorem. It's a common triangle. So this is a triangle, it's a right triangle, this angle is 90 degrees, this leg has a length of 3, this leg has a length of 4, so the hypotenuse can be found using Pythagorean theorem, and it's 5. Okay, so 5 is the length of this. So you can show the direction of a vector using an angle, as is shown for vector B. Vector B is shown to have an angle of 60 degrees made with the horizontal line here. Okay, but you can also show the direction of a vector with a right triangle like this. Now, so let's get back to what we were doing. Now I'm going in depth to explain about how to write vectors in component form, because this is the first homework set where this is what we're studying now, very basics of engineering mechanics working with vectors. Okay, so AX, the X component, we're going to start out and write the magnitude of the vector A. Vector A has a magnitude of 10. Now to get the X component, we're going to use this triangle here. Now notice the leg that has a length of 4 is parallel to the x-axis, so we're going to use a ratio of that leg over the hypotenuse of the triangle, which we know is 5. Okay, so 10 times 4/5 gives us the length of the x component of vector A. It's the length of AX. Now notice when I write vectors, I have to have the component, which is the I component here. You cannot leave that off. Okay, so that's the I component. Now what about the Y component here? This vector. Well, we know it's going to be j hat. Okay, we'll start out with the magnitude of vector A. Now times what ratio? Well, the ratio, notice the leg that has a length of 3 is parallel to the y-axis. So we use the ratio of 3/5 j hat. So here is vector A in component form. I need to go to the store and buy some good handwriting. I think would help me. And this is, we don't know the units, it's not a meters, meters per second. Temperature, I guess temperature is not a vector, sorry. Force, we don't know. So it's just, we say units. Now let's write vector B in component form. Okay. I'm first going to draw, let's use a different color, it'll get a little messy. Let's draw the two components to see what I'm dealing with. So here's vector B, here's the X component, it's BX. Now this time I'm going to draw the Y component of vector B that starts, there's BY. Now notice I started drawing it from the head of the X component, and that's okay, there's no problem with that. Now I did this so you can see this triangle here. There's a hypotenuse, one leg, another leg. That's a 90-degree angle. This angle, that's a 60 degrees there. Okay? So this is the X component. The X component is adjacent to the 60-degree angle. So for the X component, I'll take the hypotenuse, which is 10, times the cosine of 60. So take the length of the hypotenuse, that length is 10, times the cosine, because the X component is adjacent to the angle that has 60 degrees. Okay, and that's I hat. Now, is this positive or negative? So is this BX component, is it pointing in the positive X direction when it goes to the right, or the negative X direction which goes to the left? Well, it's pointing back to the left, so that's a negative, so let's can't forget the negative. Whoop. I'm sorry, I've said that the vector B does not have a magnitude of 10. It's a magnitude of 12. Let's correct that. This should be a 12 here. Okay. 12 times cosine of 60 I hat. Now what about the Y component? Well, the Y component is opposite of the 60-degree angle, opposite there. Okay, so we're going to use sine, and it's pointing in the positive. Y direction is going up because of the coordinate system that is defined for us in the problem. So I'll add 12 times the sine of 60, and that is in the j hat direction. Okay, so now that I have vector A and vector B in component form, now the resultant is the addition of these two. Okay, now when you add vectors, you can only add similar components. Okay, so that means you can only add the x components together and only add the y components together. So for the I hat, I can get the x component of the resultant vector. Let's add the x component of A, which is 10 times 4/5, plus the x component of B, notice, which is negative 12 times the cosine of 60. So all that will give me the I component of the resultant vector, plus, now let's do the j hat. There's the j component of the A vector, 10 times 3/5. And here's the j component and the y component of the vector B. It's positive, so this time plus 12 times the sine of 60 j hat. Okay, now we could leave it like that, but that's long and ugly. We might as well put that in the calculator, come out with some nice numbers here. Okay, so put that in your calculator and let me find my answer. You come out with 2I hat plus 16.4 j hat. Okay, so, but the question asks for the magnitude of the resultant vector. This is not the magnitude, this is the vector R in component form. So it's easy enough to find the magnitude then by taking the square root of the sum of the squares of the components. That's a mouthful there. Simply square the components, add them, and take the square root of that sum. Right, so the square root of 2 squared plus 16.4 squared, and that comes out to 16.51. Now I'm rounding this answer using 4 significant figures, 1, 2, 3, 4. Now you can express answers in 3 normally. I use 4 in this case. And what are the units here? Again, we don't know, so we'll just say units. Okay, so there's the magnitude using the algebraic approach. Okay, now the second part of the question asks to find the angle theta x, which R makes with the positive x-axis. Let's sketch this vector. There's the x, y. Remember, here was vector A, there was vector B, so there's the resultant vector R. Okay, let me erase that. Okay, so what we're looking for now is this angle. That's the angle theta x. So how can we find this angle theta x? Well, right triangles are some of your best friends. So let's make a right triangle. Let's use the vector R as the hypotenuse. So there's a right triangle now. Okay, there's the 90-degree angle. So I know this length is 2 and the y is 16.4. So I can say this, I know this. What if I want to find the x component, Rx? Well, I would do that by taking the length of the vector times the cosine of this theta x. Now notice theta x is the angle that the vector R makes with the positive x-axis here. So the hypotenuse times the cosine, because the leg of 2, length 2, is adjacent. The leg of length 2 is adjacent to this angle theta x. So Rx, we know that is 2. What's R? We know that And that's 16.51 times the cosine of theta x. So there's one equation, one unknown theta x. I can solve for this. Okay? Theta x is equal to the cosine inverse of 2 over 16.51. Now, this looks a lot like, this is direction, sorry about that there. This is what's called direction cosines. If a problem ever asks you to find the angle that a vector makes with a positive axis, you can use what's called the direction cosines. If you look in your notes, the direction cosine for theta x can be found by the arc cosine of whatever the x component of that vector is over the magnitude of that vector. And this can be the same for whatever component or for whatever angle you're looking for. If you're looking for the angle that theta y makes with a positive y-axis, just do the cosine inverse of the y component of the vector divided by the magnitude of the vector. Okay, sorry, back to this. Theta x, if I use this, we come out with 83 degrees there. So this angle, theta x, is 83 degrees. And so now we've done both parts, first part and the second part. This is using an algebraic solution. Hope you enjoyed, guys. Remember to write your vectors in component form. Don't forget to circle your answers and enjoy. Hope you had fun. I have to turn this thing off.